if I just give you the information of VA and V phi, that means V phase, and then give you the information here, maybe you don't understand. Why? You know, why? The difference between EA and V phase or V phi are here. You know, just remember it. Just remember that first, and then after some line we come back, we get more understanding. Okay? For example, distortion of the air gap magnetic field. Why? The difference here between the distortion of air gap, yes, of course. Yes, of course. Okay? Here, number one. Number one, distortion. So here, we have the status. Yes, maybe it's not beautiful, but I think that's okay. Yeah, this is rotors. Okay. No, sound, no. Okay. So, okay. So we have the magnetic field from the stator to the rotor. Okay, so here across the rotors. Sorry, the rotor magnetic fields across the stator. You know, yes. But this is the air gap. Right? This is the air gap. So we have another magnetic field go this way. Okay? Right? So because this magnetic field will have more distortion. So we try to shorten the air gap. So if you shorten the air gap, you can reduce the distortion, but you cannot shorten too much because when the rotor rotates, we have vibration. And if the air gap is very small, the rotor punch the stators. Boom! Damage. So we need to withstand the distortion. That is the difference between VA and V phi. Do you understand? Yes. Second one. Self-inductance. What does this mean, self-inductance? Self-inductance is L. This is inductance, right? Right? Yes? Yes. Okay, so if we have magnetic core, we have the volume. We have the volume. This is current. So we can generate the magnetic field like this. Right? Right? This one is what? Leakage flux. Do you agree with me? Leakage flux. And then we have main flux. Main flux. Okay? So we have flux totals E, the flux from leakage, plus the flux, the main flux. Okay? So this one generates self-inductance L, and self-inductance is leakage inductance plus main inductance. We say self-inductance. Okay? Yes. Yeah. So if we have more L, so if we have more L, that means more. So XL is what? XL is a omega L. So more L, more XL, more voltage drop caused by IXL. So if we have more voltage drop, more difference between EA and V phase. You understand? Also resistance, the same. You know, for here, very lucky because we assume so we ignore RA, but if we have RA, we have more voltage stroke caused by RA, so we have more difference between speed and phase. Okay? The last one we talk about silent poles. Okay, yeah, because different shaft. What does it mean different shaft? We hope we can get circular shaft. Circular shaft of the rotor. This is, you know, uniform, you know. But if we have silent like this, right? Like this, right? Okay. Yes. So now this is the areas of the rotors, right? And here we have some air gap, more air gap, more distortion. Okay, but here we use non-silent. It will be better. Because you know we only consider horn area, right? Horn area. The whole area, less distortion, you know. And if we use silent, you know, we have some space here, so more distortion. Okay, you understand? You get my point? Okay, yeah. It makes explanation. Okay. Then, yeah, this is we skip it one. It went for your reference, okay? Your reference. Let me see. Okay. Now we talk about. We cannot skip. We talk about armature reference. Okay, armature reference. Armature reference. Length long in armature reactance. So what's the armature reactance? You should read this line. Okay. Look. When a synchronous generator rotor is spinning, okay, a voltage EI is induced in the generator stated winding. So if we have a lot, we have stated current, right? Where's stated current? Or I will explain to you here. We have rotors, maybe this and the S, this the N, and we have field winding. This is positive, negative. This is IDC, or we say IF or IR rotor current, right? And so we have three phases. So this one is phase A, phase B, and phase C. Okay? This is rotor, this is stator. Okay, and I would like to make a Y connection at the stator. Okay, so I overcomer connect to B overcomer, connect to C overcomer, okay, and connect to the ground. And this is the output, right? This is the output. A. B. What else? C. Right? This is rotor, this is stator. We already have rotor current. Yes, always. Because if we have rotor current, we have magnetic rotors, magnetic field, right? Yes. Now, if we connect the load, this is load. This is output power. This is electrical power. So we have load. Okay. A, B, then C. Okay. Now, this is the closed circuit. Closed circuit, right? So we have IS, phase A current at this statement. Okay, IB and IC, you know. So IR generate VR. So now we have IS generate VS. Okay, and if we consider Lenz law, they have interactive with other. Right? We say armature reactance. So if IS is small, VS is small, so you get small distortion. Small armature reactance. So if IS increase, VS increase, we have more competitions between VI and VS. So large distortion. Okay? This is Lenz law. Do you remember Lenz law? Yes, of course. Okay, now because you are the first year student, the third year student. Okay, so look, if a load is attached to the terminal of the generator, and have a lot here, a current flows, but a three-phase static current flow will produce magnetic field out in the machine. Okay, so this stated magnetic field distort the original rotor magnetic field, right? Yeah, they have the interaction between VR and VS. Okay, so changing the resultant phase voltage. This is armature voltage. Okay, like the Newton law, right? We have Newton law number 1, number 2, number 3. This is the Newton law number 3. Okay? Do you know Newton law? Yes. Okay. Because you are very good students. Okay? Because you know everything. Yeah. Okay? Now. Okay, so we look at this paragraph, we talk about no loss condition. No loss condition. Right? No loss condition doesn't mean we don't have loss. We don't have loss. We don't have loss. We have no loss, that means we don't have VS. Okay, so no distortion. Okay? So if we don't have the current II, IIS, IDS, ICS, so if we don't have the current, that means we don't have voltage. We don't have. Right? We don't have current, so we don't have voltage drop. We don't have voltage drop. So we have the conclusion. What is this? We have the conclusion EA absolute equal to V phase absolute. Okay? Can we apply Kirchhoff? Can we apply Kirchhoff 2 for this one? Yes, if we apply Kirchhoff 2, we also get, phase voltage equation is what? EA is IA armature current times R plus GX plus V phase. Did you repeat me? Oh my gosh, my stupidness. Here is what? Here is, this is phase. This is phase. I sorry, that's me. Line voltage, okay? Yeah, sorry. Okay? So if I write here, this one should be what? VL dot. VL dot. Okay? Or we say V terminal dot. Sorry, my stupid. Okay? Just here. Okay? So we can apply Kirchhoff 2. Kirchhoff 2 for this one. Right? We can get this equation. Can you repeat it? Yeah. Okay. So for the exam, if you write equation and we forgot to put alpha dot, congratulations. You see me again next year because you are stupid. Yeah, really stupid because this is complex. For complex, we have real part and imaginary part, and we do this one. Oh my God, you challenge me. Okay, so no, you should use dot, dot, dot. Okay, yes. Okay. Cái này cái phần trưng vậy. Yeah, so if we have no lot, we don't have current, so the magnitude of AI is equal to the magnitude of V phase. Yes. What does this mean, AI? This is a internal what? Internal phase voltage. What's a V phase? This is a terminal what? Terminal phase voltage. This is internal terminal. Okay? Clear? So we know this one, right? Right. Yeah, here. This is additional generators, right? This is rectifiers, this is rotor, this is stator, and we connect the terminal of the stator to the lot. How many kinds of lots we have? 3. Resistive lot, capacitive lot, and inductive lot. Okay? Now, we have the lot. Okay? Now, lot appears. I say lot condition. I use plural. No loss condition, singular. Loss conditions, I use plural. Now we study IL fragment. Why I use S here? Answer to me, please. Why I say loss conditions? Why? Adjectivity again. 1 minute. Adjectivity. Why we use loss conditions equal? Maybe adjectivity is much more thing than I hope so. Yeah, you studied before, but now I try to make your logical thinking. Can you get answers? What is different? What are the meaning of different law? Okay. So the answer is we have three load conditions, right? First of all, we say overload. You want to get overload? No, because more temperatures, boom, say goodbye to your parents. Okay, so of course we don't need to get overload condition. So the second one is full load. Now you are intelligent. Okay, full load. Or sometimes we say rated load condition. Okay, I ask you condition, not what kinds of load we have. Very different, you know. When I mention about what kind of load, we have resistive load, inductive load, capacitive load. Now I mean load condition. And you answer to me, power factors or magnetic is strong. Because this is, you know, this is what kind of load. Yeah. And the second one, of course we don't want this condition also. This is line load. Okay, or sometimes we use under load condition. Okay? Do you understand? So, we don't want to use this one. We don't want to use this one. We have full load. You know? But the life is not a triangle. Yes? Sometimes we have overload. Sometimes we get underload. But you should know how to control. So if you have overload, we immediately reduce the load power. Okay? That means we say load shedding. Load shedding. Load shedding. If we have overload, we do load shedding. Okay? So if we have underload, what do we do? Overload, we do load shedding. So if we have underload, how can we do? Just okay. Yeah, right? Let underload condition. Right? Yes? Because underload condition, no thermal. Okay? Because underload. But you get a stupid design. You get stupid design. For example, the loss we need the load. This is the load 5 ms, and this is maybe here. This is 1 ohms, and this is 5 volt. So we just choose the conductors with 5 ampere. 5 ampere maybe 2 millimeters square. I mean the areas of the conductors. That's okay. They can withstand 5 amperes, but you get steady design. You do 5 millimeters squares for conductors. More money. You know? Understand? Yeah. In your family, you have totally 4 persons, and you pay a lot of money to buy a bus. You know? To buy the 45 seats car. Do you want? No, because you are stupid. Okay, so if your family is 4 persons, you just buy 7 seats car. That's okay. Do you know? What I have emphasized. Okay, so underload, no problem, but you show your stupidness. Okay, so full load. We have the system is full load. You know, but after sometimes for use, not in rings, you need to change or you need to upgrade the system. Okay? Yeah, that's okay. Then you know what condition will come back. So now we suppose that the generator is connected to the lagging load. Do you know for what is lagging load? Lagging load means inductive load, right? So what kind of load we have? We have resistive load. We have inductive load. We have capacitive load. Right? So this one like lagging load. Because we have L. Okay? And this one is what? Leading load. And this one we say what? Pure load. Or unity load. Okay? Yes. So now lagging. So if we have lagging, that means current is lagging to the voltage. Okay. So if here is the voltage. So here is the current, right? Because we have lagging load, the current is lagging to the voltage. And you should remember we need to follow what? Follow counterclockwise direction because we are considering electrical phase angle. Okay? Always remember that if we consider electrical phase angle, we need to follow counterclockwise direction. Okay? So I is lagging to VA. That means we are considering a lagging load. Okay? Do you understand? Đặng Chí Dũng. Okay. So, consider the blue one. The blue one is VR. Okay, and the orange is VS. You know, now we have the interaction. When the interaction between VI and VS. You know, like the theories I mentioned before. So we have armature winding. Yes, because we have we have stated current. So they will generate VS, this is VR. So the interaction between VR and VS, that is armature reaction. Okay? Yes. Okay, yeah. Of course, you need to read some description here. Now, we talk about this one. This one. This is BS. This is VR. Right? BS, this one is BS, this one is VR. Okay? So now VR is made by IR rotor current. BS made by lost current or stated current. Now we have BNet. Do you remember the BNet? BNet we discussed before, right? BNet is the cross product between VR and BS. Okay, here's the BNet. Okay, so now for armature reactance, we have this VR and this one is BS. So, you know, we need BS very small. We assume that the stated current is small, so BS is small. So we can get a BNet. Okay. So if we have more load current, more load power, more load current, so we have more BS. So that means we reduce BNet. Okay. And then if we have more lagging, more